Hello, my name is Henry Eberle, and I'll be presenting on our abstract Autonomy versus Safety in Shared Control Crowd Navigation on behalf of the team here at UCL. Shared control in crowds is a unique problem, not just the average or midpoint between a standard power wheelchair and a self-driving vehicle. A standard power wheelchair implicitly assumes that the user has the information and competence to make informed decisions and the ability to physically enact them using an input device. A shared controller system can assume neither because of the broad range of impairments that the user may have, but equally it cannot treat its user as merely cargo to be moved from A to B. Safety is the natural primary objective for shared control because prescribing organizations will not provide a power wheelchair to those who cannot prove they can operate it safely. Additionally, safety can be broken down into achievable quantities such as limiting velocity or avoiding collisions that are easily solved by an algorithm. These are beneficial to any user to some degree, because those who do not need them would be expected to drive safely anyway. But we must keep in mind that the safety measures are to preserve the self-determination of the user. Without this, the mobility will have few benefits for them. Operating in a crowd makes this balance even more complex, because it involves implicitly negotiating with many other pedestrians. You experience this any time you try and pass someone on the pavement. How many times do you both swerve in the same direction? Most pedestrians can make decisions freely on whether to act pro-socially, walking by, or selfishly, walking through someone. But when you share control with an algorithm, you give up some of this freedom. And even if you wouldn't make that choice, it doesn't mean you won't miss it. The more indirect the link between intention and action, the more difficult it is to preserve this subjective impression of being in control. Therefore, we posit as designers, we should modify the user's input or intentions as little as possible to preserve their safety. We've proposed a framework to assist us in approaching this problem with 5 levels. At level 1, only minor adjustments are made to the user input, such as correcting tremors using a filter. The user is continually involved and no outside context is required. Level 2 is similar, except that the wheelchair can act for short periods without user input. This is useful for input devices such as head arrays that are fatiguing to be continually used. At level 3, outside sensors are used to detect context and either avoid obstacles and or optimize an objective function. An example of this would be virtual force field methods. By level 4, the user does not directly drive the wheelchair, but selects between trajectories generated by the controller itself. At level 5, the controller infers user intent, either from an input device or a passive sensor, and chooses the trajectory it considers most likely to fulfill their goals. Currently, the framework is input device agnostic, but a second axis representing the difference between input devices could give greater precision. Additionally, given that many published methods occupy somewhere between levels 4 and 5, further subdivisions may be necessary in that area. Nevertheless, we believe it is a good rule of thumb to choose as low a level as possible to ensure the minimum level of safety for the user. Thank you for listening. We have some additional time for questions if anyone has any.